In this video, I am going to talk about asynchronous transfer mode network. What is asynchronous transfer mode? In late 1980s, the world's telephone companies finally began to realize that there was more to telecommunications than transmitting voice in 4 kHz along channels. It is true that data networks such as X.25 existed for years. After much study, a hybrid form of using a fixed size blocks over virtual circuit was chosen as a compromise that gave reasonably good performance for both types of traffic. This method, called ATM, asynchronous transfer mode, it has become an international standard and is likely to play a major role in future distributed system, both local area ones and in wide area network also. Circuit switching versus packet switching. Circuit switching is a connection oriented, which establishes a dedicated path between the hosts. Data can flow continuously over the connection. Packet switching, which divides the messages into fixed size units, which are routed through the network individually. Different packets in the same message may follow different routes. ATM network. ATM uses fixed size packets called cells. Each 53-byte ATM cell contains 48 bytes of data payload and 5 bytes of control and routing information in the header. The header provides addressing information for switching the packet to its destination. The payload section carries the actual information, which can be data or voice or video. The payload is properly called the user information field. The reason for choosing 48 bytes as a payload sizes to compromise between the optimal cell sizes for carrying voice information and data information. The characteristics of asynchronous transfer mode networks. It uses small and fixed size cells. It is connection oriented and it supports multiple service types. It is applicable to LAN and WAN also. How does the ATM network is working? This scheme or this method has a number of advantages over traditional packet and circuit switching. The most important one is that a single network can now be used to transport an arbitrary mix of voice, data, and broadcast television, video tapes, radio, and other information efficiently, such as telephone, X.25, cable TV, and etc. New services such as video conferencing for businesses will also can use it. In all cases, what the network is cells. It does not care what is inside them. This integration represents an enormous cost saving and simplification that will make it possible for each home and business to have a single wire coming in for all its communication and information needs. It will also make possible new applications such as video on demand, teleconferencing, and access to thousands of remote databases. ATM reference model. ATM has its own protocol hierarchy as shown in the diagram. The physical layer has the same functionality as layer 1 in the OSI reference model. The ATM layer deals with the cells and cell transport, including routing. So it covers OSI layer 2 and part of layer 3. However, unlike OSI layer 2, the ATM layer does not recover lost or damaged cells. The adaptation layer handles breaking packets into cells and reassembling them at the other end, which does not appear explicitly in the OSI model until layer 4. The service offered by the adaptation layer is not a perfectly reliable end-to-end service. So transport connection must be implemented in the upper layer, for example, by using ATM cells to carry the TCP IP traffic. ATM physical layer. An ATM adapter board plugged into a computer can put out a stream of cells onto a wire or fiber. The transmission stream must be continuous. When there are no data to be sent, empty cells are transmitted, which means that in the physical layer, ATM is really synchronous or not asynchronous. Within a virtual circuit, however, it is asynchronous. Alternatively, the adapter board can use SONET, synchronous optical network, in the physical layer, putting its cells into the payload portion of SONET frames. The virtue of this approach is compatibility with the internal transmission system of AT&T and other carriers that use SONET. In Europe, a system called SDH, synchronous digital hierarchy, that is closely patterned after SONET is available in some countries. The SONET uses a basic transmission rate of 51.84 Mbps. It is a basic unit of consisting of 9 by 90 array of bytes called a frame. The frame is divided into two areas, transport overhead and synchronous payload envelope. The ATM layer, the end result was a 48 byte cell, which no one really liked. It is too big for voice and too small for data. To make it even worse, a 5-byte header was added, giving a 53-byte cell containing a 48-byte data field. The cell header layer, the layout of a cell header from a computer to the first ATM switches shown in this diagram. Unfortunately, the layout of a cell header between two ATM switches is different, which with the GFC field being replaced by 4 more bits for the VPI field. In the view of many, this is unfortunate since it introduces an unnecessary distinction between computer to switch and switch to switch cells and hence adapter hardware. Both kinds of cells have 48-byte payloads directly following the header. The GFC um, may be used for flow control. If an agreement on how to do it, it can be achieved. The VPI and VCI fields together identify which path and virtual circuit a cell belongs to. Routing tables along the way use this information for routing. These fields are modified at each hop along the path. The purpose of the VPI field is to group together a collection of virtual circuits for the same destination and make it possible for a carrier to reroute all of them without having to examine the VCI field. The payload type field distinguishes data cells from control cells and further identifies several kinds of control cells. The CLP field can be used to mark some cells as less important than others. So, if congestion occurs, the least important ones will be the ones dropped. Finally, there is a 1-byte checksum over the header is also used. ATM adaptation layer. At 155 Mbps cell can arrive every 3 milliseconds. Few, if any, current CPUs can handle in excess of 3 lakhs interrupt per second. Thus, a mechanism is needed to allow a computer to send a packet. You have the ATM hardware, break it into cells, transmit the cells, and then have them reassembled at the other end, generating one interrupt per packet, not per cell. This disassembly or reassembly is the job of the adaptation layer. It is expected that most host adapter boards will run the adaptation layer on the board and give one interrupt per incoming packet, not one per incoming cell. Unfortunately, here too, the standard writer did not get it quite right. Originally, adaptation layers were defined for 4 classes of traffic. Number 1, constant bitrate traffic. Number 2, variable bitrate traffic, but with a bounded delay. Number 3, connection-oriented data traffic. Number 4, connectionless traffic. ATM defined 4 versions of ATM adaptation layer. Quickly, it was discovered that classes 3 and 4 were essentially the same. So, they were merged into new classes 3 by 4. At that point, the computer industry woke up from a short nap and noticed that none of the adaptation layers were suitable for data traffic. So, they drafted AAL5 for computer to computer traffic. The AL interface was initially defined as classes A to D with the SAP service access points for AL1 to 4. AL3 and AL4 were so similar that they were merged into AL3 4. The data communications community concluded that AL3 for 4 was not suitable for data communication applications. They pushed the standardization of AL5. AL2 was not initially deployed. AL type 5 protocol, SEER, simple and efficient adaptation layer. The main functions of AL5 are segmentation and reassembly. It accepts higher level packets and segment them into 48-byte ATM cells before transmission via ATM network. AL5 is a simple and efficient AAL to perform a subset of the functions of AL3 and 4. The CPCS-PDU payload length can be up to 65,535 octets and must use pad to align CPCS-PDU length to a multiple of 48 octets. Seal. We will focus on the seal due to its simplicity. It uses only one bit in the ATM header, one of the bits in the payload type field. This bit is normally 0, but is set to 1 in the last cell of packet. The last cell contains a trailer in the final 8 bytes. In most cases, there will be some padding with zeros between the end of the packet and the start of the trailer. With the seal, the destination just assembles incoming cells for each virtual circuit unit. It finds one with the end of the packet bit set. Then it excites and processes the trailer. The trailer has 4 fields. The first 2 are each 1 byte long and are not used. Then comes a 2-byte field giving the packet length and a 4-byte checksum over the packet, padding and trailer. ATM switching. The ATM network are built of copper or optical cables and switches. The figure shown on the screen, which is illustrating a network with 4 switches. Cells originating at any one of the 8 computers attached to the system can be switched to any of the other computers by traversing one or more switches. Each of these switches has 4 ports, each used for both input and output. Inside a generic switches shown on the figure on the right side of the diagram, the B diagram, it has input line and output line and a parallel switching fabric that connects them. Because a cell has to be switched in 3 milliseconds, and as many cells as there are input lines can arrive at once, parallel switching is essential. ATM switching. The cells originating at any of the 8 computers attached to the system can be switched to any of the computer by traversing one or more switches. Each of these switches has 4 ports, each used for both input and output. It has input lines and output line and a parallel switching fabric that connects them because a cell has to be switched in 3 seconds, and as many cells as there are input lines can arrive at once. Parallel switching is essential. Head-up line blocking. The problem is when 2 cells arrive at the same time on different input line and need to go to the same output. Head-off line blocking in computer networking is a performance limiting phenomena that occurs when a line of packets is held up by the first packet. If 2 ports each have a stream of cells for the same destination, input queues will build up blocking other cells behind them that wants to go to the output ports that are free. The solution is a different switch design that copies the cell into a queue associated with the output buffer and lets it wait there instead of keeping it in the input buffer. The other solutions are only the time division switches or space division switches. Implications of ATM. Some implications of ATM for distributed system. The availability of ATM networks at 155 Mbps, 622 Mbps, and potentially at 2.5 Gbps has some major implications for the design of distributed system. The reason is due to sudden availability of enormously high bandwidth, the effects are most pronounced on wide area distributed system. Consider sending a 1 mbit file across the United States and waiting for an acknowledgement that it has arrived correctly. For 1 mbit, takes a bit about 50 milliseconds to go across the US. At 64 kbps, it takes about 15.6 seconds. As speeds go up, the time to reply asymptotically approaches 30 milliseconds. For messages shorter than 1 Mbps, which are common in distributed system, it is even worse. ATM switching is continued. The conclusion is For high-speed, wide-area distributed system, new protocols and system architecture will be needed to deal with the latency in many applications, especially interactive ones. The flow controller, a truly large file, say a video tape consisting of 10 GB. A client-server model. The OSI model has some drawback. The existence of all those headers generates a considerable amount of overhead. Every time a message is sent must be processed by about half a dozen layers, each one generating and adding header on the way down or removing and examining a header on the way up. On wide area network, the number of bits per second that can be sent is low, so this overhead is not serious. Client server model, learn burst distribution. While ATM networks are going to be important in the future, for the moment, they are too expensive for most applications. So let us go back to more conventional networking. At first glance, layered protocols along the OSI line look like a fine way to organize a distributed system. The client server model. This is something is often the client server model that we introduced in the previous one. The idea behind this model is to structure the operating system as a group of cooperating processes called servers that offer services to the users called the clients. The client and server machines normally all run the same microkernel with both the clients and servers running as user processes as given earlier. A machine may run a single process or it may run multiple clients, multiple server or a mixture of two. Based on the simple connectionless request reply protocol, the client sends a request message to the server asking for some service. Something like an example is read a block of a file. The server does the work and returns the data requested or an error code indicating why the work could not be performed. Advantage is very simple. The client sends a request and gets an answer. No connection has to be established before use, and the reply message serves as the acknowledgement to the request. The efficiency is the protocol stack is shorter and thus more efficient. Only 3 levels of protocols are needed. The physical and data link protocol take care of getting the packets from client to server and back. No routing is needed and no connections are established, so layers 3 and 4 are not needed. Layer 5 is the request reply protocol. There is no session management because there are no sessions. The upper layers are not needed. The communication services provided by the kernel can be reduced by 2 system calls, one for sending messages and one for receiving them. These system calls can be invoked through library procedures send and receive. Send sends the message pointed to by M pointer to a process identified by the destination and causes the caller to be blocked until the message has been sent. Receive is another process, causes the caller to be blocked until a message arrives. Client and a file server in C, both client and the file server need to be shared some definitions collected into a file called header.h. Both the client and server include these using the hash include statement. It has the effect of causing the preprocessor to literally insert the entire contents of header.h into the source program just before the compiler starts compiling the program. Example for client and server. To provide more insight into how clients and servers work in this section, we can present an outline of a client and servers in a C program. Both the client and the server need to share some definition. So we will collect these into a file called header.h, which is shown on the screen. Both the client and server include these using the header.h. The statement has the effect of causing a process to literally insert the entire contents of header.h into the source program just before the compiler starts the compiling program. Let us first take a look at header.h. It starts out by defining two constants, max-path and buffer-size. In this screen, you can see the max-path and buffer-size. and that determines the size of two arrays needed in the message. The former tells how many characters a file name may contain. The latter fixes the amount of data that may be read or written in one operation by setting the buffer size. The next the constant file underscore server provides the network address of the file server so that clients can send messages to it. So second group of constant defines the operation number. These are needed to ensure that the client and server agree on which code will represent a read, which code will represent a write, and so on. We have only shown 4 here, but in a real system, there would normally be more number of operations. If, every reply contains a result code. If the operation succeeds, the result code often contains useful information. If the operation is unsuccessful for some reason, the result code tells why using code such as e underscore bird, I underscore opcode, comma, e underscore bird underscore param, PRAM, and so on. Finally, we come to the most important part of header.hs, the definition of the message itself. In this example, it is a structure with 10 fields. All requests from the client to the server use this format. In a real-time system, one would probably not have a fixed format message, but it makes the explanation very simple here. For a client to send a message to a server, they must know the server's address. In the example of the preceding section, the server's address was simply hardwired into header.h as a constant. This strategy may work in a simple system. More sophisticated form of addressing is needed. File server has been assigned a numerical address 243, but not really specified what this means. Does it refer to a specific machine or to a specific process? Sending kernel can extract it from the message structure and use it as a hardware address for sending the packet to the server. Build a frame using the 243 as a data link address and put this frame out on the LAN. Server's interface would see the frame, recognize 243 as its own address, and accept it. If only one process or destination machine, the kernel will give it to the one and only process running there. If there are several processes running on the destination machine, the kernel has no way of knowing which one gets the message. Only one process can run on each machine, which is a serious restriction. Addressing mechanism. Alternative addressing system sends message to processes rather than machine. How processes are identified? One common scheme is to use two part names specifying both the machine and the process number. Thus, 243.4 or 4 at 243. Machine number that is used by the kernel to get the message correctly delivered to the proper machine. Process number is used by the kernel on that machine to determine which process the message is intended for. Advantage of this approach is every machine can number its processes starting at 0. No global coordination is needed because there is never any ambiguity between process 0 on machine 243 and process 0 on machine 199. The former is 243.0 and the later is 199.0. An alternative addressing system sends message to processes rather than to machines. Although the method eliminates all ambiguity about who the real recipient is, it does introduce the problem of how processes are identified. One common method is to use the two-part scheme specifying both a machine and a process number. As I told you, the 243.4 or 4 at 243 or something similar designate process 4 on machine 243. The machine number is used by the kernel to get the message correctly delivered to the proper machine, and the process number is used by the kernel on that machine to determine which process the message is intended for. The nice feature of this approach is that every machine can number its process starting at 0. No global coordination is needed because there is never any ambiguity between process 0 on machine 243 and process 0 on machine 199. The former is 243.0 and the later is 199.0. This is shown on the figure. Process addressing with broadcasting. Machine process addressing is not transparent since the user is obviously aware of where the server is located, and transparency is one of the main goals of building a transparent system. Example is, suppose the file server normally runs on machine 243, but if that machine is down, the machine 176 is available, but program previously compiled using header.h all have the number 243 built into them, so they will not work even if the server is unavailable. Clearly, this situation is undesirable. An alternative approach is to assign each process a unique address that does not contain an embedded machine number. And to achieve this, a centralized process address allocator that simply maintains a counter can be used. Upon receiving a request for an address, it simply returns the current value of the counter and then increments it by 1. The disadvantage in the scheme is centralized components like this do not scale to large system and should be avoided. Another method for assigning process identifier. To let each process fix a down identifier from a large sparse address space, such as the space of 64-bit binary integers. The probability of two processes picking the same number is tiny, and the system scales well. The problem is, how does the sending channel know what machine to send the message to? On a local area network, that suppose the broadcasting, the sender can broadcast a special locate packet containing the address of the destination process. This method is shown in the earlier diagram 2.10b.